online. Shifting to Zoom gives us a great opportunity, I think, to hear from speakers from all over the country. So in the coming months, we're going to hear, next month it's going to be Pittsburgh. We've got in January, we've got a speaker in Chicago. In February, our speaker will be in Wisconsin. In March, our speaker is going to be in North Carolina. So it also allows those of you who are snowbirds to be able to tune into Grosse Pointe Audubon meetings from wherever you are around the country, which is going to be great. Before I go any further, I'm going to urge those of you that your screen is on and we can see you. And if your microphone is on, we can hear you. So we can hear and see what's going on in the background. Please make sure that you hit the mute button on your screen to make sure that your microphone is off when our speaker gets started, because we don't want to hear, you know, dogs barking and people talking and rustling of papers and things. But you can always turn those back on at the end of the meeting so that we can ask questions of our speaker. And now it's time for me to introduce the other members of the band. Our vice president and on saxophone is Mark O'Keefe. On lead guitar is our treasurer, Trina Bresser-Matus. On drums is our secretary, Anna Werfel. And as backup singers are our board of directors, it's Mike Florian, Joanna Pease, Terry North, and Robert Walter. I think I got everybody.
Ooh, 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 ooh.
What, Ed?
Ooh, ooh.
What, Ed? What?
Facebook.
Facebook. Yes. Thank you. And our CEO, CFO, and CCO of Facebook is Ed O'Keefe. Thank you, Ed. Ed McHale. Ed McHale. Yeah, I'll get it right sooner or later. Thank you for the reminder, Ed.
Okay.
One other thing about the officers of the board, we couldn't have an election in April for our annual meeting because, as you know, we canceled our March and April meetings. So we're going to attempt to have a meeting by mail or by email coming up or electronically coming up on or about October 1st. Judy Florian has created a nominating committee. If you have any interest in serving as an officer or board member for Grosse Pointe Audubon, please, please, please let me or Judy know ASAP so we can put together the election. Treasurer's report, Trina.
Well, I'm sure a lot of people are getting tired of Zoom meetings. This is our first for Grosse Pointe Audubon. But one of the upsides is that we have not had any expenses. So we currently have $2,672 in our bank account. We've had just over $1,000 in dues since Bill put the notice out last month. So we're doing well.
All right. And speaking of treasurer's report, one thing we did over the summer at Ed McHale's suggestion was to make it easier for you to pay your dues. If you do at Venmo on your smartphone, you can now pay your dues electronically. Open your Venmo app and press the play or request button down in the bottom right-hand corner. And at the top of the next page, type in GP Audubon, capital G, capital P, space, capital A, Audubon. It will show up as at GP-Audubon. Plug in the amount, say what it's for, and hit pay, and you're done. Trina will get an email telling her that the money has been sent. Thank you very much. We talked a little bit about the Ford House earlier. There are no bird walks scheduled for the Ford House, but we still encourage you to be socially, go birding there socially responsibly, or anywhere else of your choosing. It is free for Ford House members to walk the grounds. If you're not a Ford House member, it will cost you a $5 fee. You do have to receive a grounds ticket in advance. So you have to log on to their website and buy a ticket. They will send it to you by email. When you pull into the Ford House, you hold up the ticket to the window of your car. They will scan it, and they will also want to see that you have a mask. Let's see what else. Oh, I had a conversation with one of the groundskeepers at the Ford House a couple of weeks ago. He's also a birder, and he said that the spring migration at the Ford House this year was phenomenal. Figures, right? Bird sightings. I know Eddie has a bird sighting that he wants to share with us.
Yes, broadwings. 6,600 broadwings at Point Moulet between 2 o'clock and 4:30, a few days back.
Yep, broadwing migration is actually tailing off right now, but 6,000 birds in a day is just.
I was there September 17th, and that is historically a big day for broadwings. Even the vets were impressed.
They were right on time.
Yeah.
Robert, I understand you saw something that you wanted to share.
Sunday morning, I played the Gentler Park golf course, and there was a pied-billed grebe swimming around one of the ponds and diving in it. Just one, but it was a nice sighting. There's also a pair of red-tailed hawks with a nest on that golf course. And this summer, 2 robins built a nest on top of a drain pipe under the eaves on the side of my house and successfully had two broods of young, two in each one. So I could stand on the side by the side door and watch the robins feeding the young ones, which was quite cool.
Cool. I hope that next time you go golfing, you'll be able to see more than one birdie. Jim, did you have something that you wanted to share? No, I guess not. Anybody have any good birds that they've been seeing?
Bill,
Yes, Judy.
Mike and I are currently in upstate New York at my sister's country house, and she has this crazy raven that's been pecking at the screens at her window.
Wow.
So,
How far upstate? Are you guys in the Adirondacks?
no, she's around Cooperstown area.
Oh, wow.
And this raven is one big dude, I'll tell you. He wants to be noticed. But my question to you is he pecking at the screen because he wants that for his nest? Because they wouldn't be nesting now, right?
No, I don't think so. We're going to ask Roseanne, and hopefully she'll have an answer for us. Maybe Roseanne could text us an answer. She might know something about it.
Okay.
It could be the fact that it may have been a rival, that he was in the mirror image. Was I mute? Am I muted?
Oh, we hear you, Jim.
Okay, I'm not sure but it may have been looking at another bird.
Right.
No, he was looking at his reflection in the window is what he was
Yeah.
saying.
Yeah.
And that was,
He was also tearing the screen apart at the same time.
Maybe
Judy, send me a picture.
Too late, he's already gone. If he comes back, I'll get one.
Great. He's probably around.
Oh yeah, we heard him today.
All right. So we said that we'd get started with our speaker tonight around 7:40. It's 7:39 right now. Sorry, Dr. O'Malley, we're throwing you under the bus. I hope you're ready.
I'm completely ready.
Okay.
I'm a little confused though, because the thumbnails I see of the people who have responded so far, are they the only ones who are logged into the meeting?
We have 35 participants, and there are a whole bunch of people.
Okay, whose
So if you click on the
thumbnails I don't see?
right, if you click
Okay.
on the little blue arrow on either
Yeah.
side, that will take you down the line.
Oh, there we go. I see. All right.
Who else
Good.
is
Okay,
there?
that's fine. Yeah, great. Okay, so ready to go?
Yeah, Ed O'Malley is a pediatric ophthalmologist here in Grosse Pointe, but I'm going to let Ed introduce him because Ed apparently has known Dr. O'Malley for a long time.
Well, it's with great pleasure that I introduce Ed O'Malley. Ed and I graduated from Detroit Cathedral High School in 1967, an all-boys Catholic school. And we kind of lost track of each other, but then recently got back in touch. And we've got together a couple times, done some fun things. And he talked about this topic of a presentation. And over the last 12 months, it kind of came to fruition, and here we are today. So with great pleasure, I introduce Ed O'Malley.
Well, thanks, Ed. I thought I knew something about bird vision until I started doing the research for this talk. And then I realized I really didn't know very much about it, but I know a lot about human vision, and it was easier to understand the avian physiology. So without further ado, let me get my PowerPoint up. And there it is. All right, full screen. All right, here we go. This is about how we see birds and how birds see us.
Ed, I'm not sure I can see it.
Whoa.
Can everybody else see it? I'm still looking at you. Ed.
Okay, I've got it on my screen, so let's figure out what's going on.
Did you click share screen, Ed?
At the bottom?
The bottom, the green share screen. I gave you privileges to do that.
Oh, no, I didn't.
Yeah.
So
Gotta click
let
that
me,
green button.
It's a two-step process.
all right, here we go. Let's try this again. All right. The share screen is, hold on. Can I get this out of the way? I lost you guys. So let me
Yeah,
get
no
you-
big deal. So just go up to
Well, what is this?
where next to Zoom US, it'll say meeting.
Okay, yeah, I lost that Zoom, so I'll just go, I'll log in again. Here we go. All right, so share screen, got it. And it is with the PowerPoint. Here we go. Good. Yep, share.
Bingo.
Just
There it
like
is.
downtown.
There you go.
Okay. And we need to get
You can't click
you.
You can click it, nothing will happen to you. The key has been clicked.
All right. Now,
There we go.
we
Looks
in good
good.
shape? Good. So this is about how we see birds and how birds see us. Today, we're going to talk about light, color, and vision. It's a long story. It's almost 14 billion years long. And so this is now, hold on to your hats. Here's my special effect coming up. This thing began with the Big Bang. Thanks. You don't have to applaud. Okay. The Big Bang was the birthday of the four forces of nature. Gravity, which, as you know, keeps the Australias from falling off the world. The strong force, which holds the nuclei of atoms together. Weak force holds the electrons in their place. And electromagnetism, which is the subject of our talk today. Electromagnetism is the branch of physics that deals with charged particles in motion. So charged particles either create a magnetic field, or if you make them oscillate, they emit radiation, gamma, light rays, X-rays, etc. It's usually shown like this as a spectrum. It goes from the left side, long wavelength, low energy radio waves, to the other end, short wavelength, high energy gamma rays. A friend of mine just had surgery with a gamma ray knife the other day. In the middle of this electromagnetic spectrum is a very narrow area of energy called the visible spectrum. We call it the visible spectrum because we can see it. If we were Superman, the visible spectrum would extend into the X-ray area. And we're going to talk about how birds see the visible spectrum and beyond. So the energy reaches Earth mostly from the sun, but there's background radiation left over from the Big Bang. In addition to the light rays, the visible rays that come from the sun, there are other forms of invisible radiation. So the light bangs off buildings and sidewalks until eventually it reaches the retina of this skateboarder. It excites a chemical in the retina, which creates an electric impulse, goes down the optic nerve, through the midbrain to the visual cortex, where it allows the skateboarder just in time to turn before he gets run over by the fire engine. So vision is really a very important function of all organisms. In fact, 530 million years ago, the trilobite had a compound eye. This is the oldest known fossil of an eye. So it's really useful. And you might ask, well, what's so useful about it? Well, one of the ways we know it's useful is that we've had 5 mass extinction events. And every time the organisms that are left over that evolve to the next mass extinction event evolve vision. Why vision? Well, currently 95% of the species on Earth have vision. And it enables them by means of sunlight to excite their hormone producing organs and the so-called circadian rhythms, cortisol and thyroid, a number of different organisms get a number of different organs secrete hormones based on the input that comes through the visual system to those organs. It enables the organism to have photolocomotion, that is the ability to swim toward light or away from light, enables it to find food and to avoid becoming someone else's food. So how does this happen? Natural selection. It's all just natural selection. And how does natural selection work? The same way our computer works, almost. Select, copy, paste, save, select, copy, paste, save. But you know, you can do this on your computer and your millionth copy is exactly the same as your first copy. But remember back in the days of Xerox machines, when you have certain forms that you want to, you'd print up 100 of them, and then when you'd run out, you'd print up another 100 of them. You better use the original when you make your prints, because if you're printing from prints, pretty soon you've got something that's unreadable, because each time there's a little degradation of the quality of the copy. And the same thing happens with humans and animals and any cellular division. Cellular division is fraught with error. And these errors are called mutations. Mutations that change in the structure of a gene, and they occur more or less randomly throughout the genome. The thing about the genome is most of the DNA in the nucleus of a cell is non-coding. It's structural DNA. It just holds up the DNA that is the important DNA that codes for protein. And mutations can occur anywhere in this system. And if it occurs and produces a different protein that gives the organism a competitive advantage, it tends to stay in the genome. If it's a disadvantage, then it tends to go out of the genome. So mutations, you tend to think about, oh, he had a mutation. That sounds like a bad thing. Well, if it weren't for mutations, we would be still in the primordial soup. The only way you get out of the soup is you have enough mutations that enable you to have an advantage that changes the organisms, that goes from, you know, unicellular life to a very complex life that we enjoy now. And it happens because there's an interaction between the physical environment, whatever it is. Physical environment can be defined a lot of different ways. I'll use one example, but the physical environment pushes against the organism as it is evolving, and there are mutations that occur more or less randomly. If the physical environment happens to be the ocean and mutations are occurring randomly, they are either favorable or unfavorable. But it turns out that if you're an ocean dweller and it's several 100 million years ago, it doesn't matter whether you start off a fish or a reptile or an aquatic bird or a mammal, you kind of evolve a shape that works, and it's the shape of a torpedo. And the way this works is that 37 trillion cells in the human body are undergoing replication hourly, daily, weekly, and sometimes every decade, depending on the length of the cell's life. So all these cells are mutating in vast numbers. So little changes happen, and the little changes that happen that help the organism stay in the genome. This is an early Paleozoic unicellular organism. And you'll see right here, this is something called the eye spot. Some of these organisms evolved light-sensitive cells that responded to light and sent messages elsewhere within the cell. Turns out the Euglena has one of these eye spots. Oops, sorry. Euglena has an eye spot right here. And mitochondria is the energy factory of the cell. The eye spot sends some message to the mitochondria to produce energy that causes the flagellum to beat, and it does, and these cells can beat toward light or away from light, whichever happens to be adaptive for them. The singular eye spot is shown in duplicate here in the planaria. So we have 2 eye spots, and those 2 eye spots are better than 1 because they at least give this organism a little sense of where the light is coming from. But the really great thing happened when some of these organisms evolved invagination of the eye spot. You think, well, why is that so important? Well, because if you're invaginated, then you can tell really which direction the light's coming from. Huge advantage competitively. So time goes on, millions of years pass, and this invagination becomes a pit, and it actually becomes like a little pinhole camera. And in fact, this is exactly the structure of the chambered nautilus eye. Some organisms developed a cornea. Cornea is a clear proteinaceous material that helped the eye to resolve light. Others went on to develop lenses and fluid in the eye. Meanwhile, the retina is undergoing differentiation, getting a lot more complicated as the brain is getting a lot more complicated. And before you know it, bingo, sense of vision. So we're going to talk about this sight that we have, that we enjoy, and talk about image resolution, color perception, motion detection, and the visual field. So image resolution, that is, how clear is the image, is based on the clarity and the focusing ability and photoreceptors that can catch this clear image that's been focused. We think of the cornea and lens and vitreous like panes of glass or focusing elements that need to be clear in order for the image to be clear on the retina. This is an Indian green parrot who had injury to her eye. And you can see this is a cataract right here, back here, this gray spot up here, kind of brownish. This is iron blood staining. So this bird had bleeding inside the eye, and when the blood was absorbed into the retina, the iron in the hemoglobin stained the cornea. And this eventually goes away. It absorbs from the outside in. We see this in humans when humans have injuries to the eye. A few hockey players this season have had this injury. It's put them out of action for a month or so during the shortened Stanley Cup playoffs. So we have focusing, which depends on the physical phenomenon of refraction. And focusing of an image depends upon the light passing from a medium of one density to a medium of a different density. So you'll see this shows the eyeball looking into the water, and indigenous people would hunt fish with arrows, and they knew that they shouldn't aim their arrow at this guy because that fish wasn't there. They knew instinctively, or with trial and error, that the fish was actually here because when the light passes from air to water, it bends. And that's how the eye focuses. The eye is a spherical focusing mechanism where the light goes from the air to the water density of the eye, and it is bent. So if you look here, this is an eye with normal focus. Parallel light rays enter the front of the eye, are brought to focus right on the retina. Here we've got a nearsighted eye that light rays are brought to focus in front of the retina. This is a farsighted eye brought to focus behind the retina. Now, a farsighted eye has the ability of correcting this because you can strengthen the focusing of the lens by rounding out this lens and making it more spherical and making it a stronger focusing element. Well, in a chick on day 14, excuse me, the chick rotates in the shell such that the head is toward the large end of the egg. And on day 18, the chick rotates so that the right eye is up against the shell, the left eye is down against his body. And it turns out that the stimulation through the shell of light causes that right eye to become myopic or nearsighted. The left eye is hyperopic or farsighted. It's always the right eye nearsighted, left eye farsighted, never the other way around. And you wonder, well, why is that a good thing? Well, in humans, when that happens, we put glasses on them. And this is a child who has very nearsighted right eye and a farsighted left eye. And with the competition between the two eyes, the brain that is undergoing development is going to pick out the best image, and that image is going to have the pathways more thoroughly differentiated. If the eye is not used during a critical period of early life, it doesn't tend to develop vision as well. So this is a nearsighted eye and a farsighted eye, and chickens use their farsighted left eye, tilt their head to look up, to be aware of birds of prey, and they use their nearsighted right eye to look down to see the food. So a very useful adaptation. Accommodation is the ability of the eye to change focus from a distant object to a near object by altering the shape of its refractive apparatus. In humans, it's changing the shape of the lens. Now, this is a diagram of distance vision in an eye that is perfectly well focused. Parallel light rays coming from a far distant target are refracted by the front of the eye, the cornea, that's this guy here, cornea, and the lens, brought to focus right on the retina. A happy situation. You bring the object of interest close to the eye. Now they are not parallel light rays, rather they are divergent light rays. So divergent light rays are going to not be focused on the retina unless you do something to this lens. So we can round out the lens, look at the difference between this and this, strengthening the focusing of the eye, the power of the eye, and put the focus on the retina, which is a really good thing to have. This is, it's not completely intuitively obvious, but I will explain this to you and hope I can be clear enough. The natural state of the lens of the eye is spherical. If you take the lens out and put it down on the table, it rounds out. But in the eye, it is held taut. It's stretched to be flat. And the only way you can get it back to its normal state is you have to focus these eye muscles here called ciliary muscles, and it's a sphincter. This is the front view of it. A sphincter muscle is one that closes and opens, relaxes and opens. So as you focus your eye at near, you focus this sphincter, which relaxes the tension on these connecting zonules that hold the lens in place. And then it allows this lens to round out and become more powerful. So that's how it is we read. Now, the reason that almost everybody I see in my thumbnails has reading glasses or bifocals is that this lens loses its elasticity throughout life. And when you focus it, when you squeeze on that sphincter and ask that lens to round out, it doesn't do it because it just loses it's lost elasticity. So there's a very important application of this phenomenon to birds, to aquatic birds. So you've got some dabbling ducks here, and you've got a kingfisher. And so what happens when they duck their face underwater and they lose that air-water interface between the air and the water interface of their cornea? Well, now it's a water-water interface. And it turns out they lose like 45 diopters of plus power, a huge amount of focusing power. So they would be in a bad way. You know, when you go in a swimming pool, open your eyes, things are really blurry. Put goggles on, things are very clear because you've restored the air-water interface between your eye and the outside world. So what happens is these birds have, again, remember, it's all about the interface between light and between air and water. These birds have the ability not only to round out their lens, but they've got muscles that stretch into the cornea, and they actually can steepen the cornea. So it's a really amazing thing. Humans don't do this, aquatic birds do. And this is courtesy of the University of Tennessee, where they get 1 point off for spelling here. There are 2 M's in accommodation. But there's a rule in giving talks is you never can find any typo or spelling error until it's projected like 30 by 60 feet on a screen in front of 5,000 people. But this is, so we're talking about image resolution. So now we've got a clear medium and we've got a focusing element. You got a cornea and a lens that focuses it. now you need something to catch that focused image. And the retina has several different kinds of photoreceptors. In humans are trichromats. It means we have 3 different cone systems, but organisms can be monochromats, dichromats like dogs, trichromats like humans, tetrachromats like some birds and other animals, and pentachromats like many birds. So most birds have 5 different systems for seeing, 2 more than we have. Both have rods. Rods are, they see only in black and white. They're dispersed throughout the retina, and they're really good for peripheral vision, very good at identifying movement. And then there are some other photoreceptors that see in the ultraviolet and the infrared and elsewhere. So this is, these are 3 curves which show the cone response to different wavelengths of light. So if you're down here around 450, you will excite the short wavelength cones. Those are the blue cones. Over here, 600 or so, 600 or so. The long wavelength cones, those are the red cones. And in between, we have the green cones. So the cones are responsible for the color spectrum. It requires bright light. It gives the user high acuity, high resolution, and they are highly densely packed into the fovea of the eye. F-O-V-E-A, fovea. It's a Latin word. It means pit. The rods see only in black and white. They require very little light, great for motion detection, poor at resolving, and they're found in the peripheral retina. So if you go into a dimly lit room and you're looking around for something, it's over there, but you don't see it when you look at it. You look a little bit next to it and you can see that image because you're stimulating the rod vision in dim light. So these are the 2 curves of rod and cone vision. The cone vision is averaged, and the rod vision you can see responds more to the high energy, shorter wavelength lights. But wait, folks, there's more. This is a slide that I showed this lecture yesterday to my family and my grandson, who's 9. When he finished, all he could remember is double cones with a drop of oil and red-green filtered glasses. And so it worked. That's what I want you to remember. So this is a schematic of the bird pentachromatic retina. So light is coming, the yellow arrows refer to the direction of light, comes from the bottom to the top, passes through a lot of stuff to get to the outer segments where the action is. So the outer segments here is where the chemical reaction occurs. And the interesting thing is that in addition to red, green, and blue cones like we have, they also have a double cone system, and they have UV cones. So the double cone system, and of course they have rods, like mammals, humans. And the double cones are found, besides in fish, in reptiles and others. They are luminance detectors, so they will tell the retina something about how bright the image is to turn on certain of the connected cells. They are good for motion detection. Usually we think of rods as being a motion detector, but the double cones are motion detectors. But this is the really cool thing, is they see polarized light. So they are able to polarize light, which those of you who are fly fishermen know that if you don't have polarized sunglasses, you're going to watch everybody else catch fish, because you need to be able to see the fish rising in the water. And so these birds who hunt fish are able to see the fish way better than somebody who doesn't have this cone system. So they can see through the water to see the fish. And so they have, in addition to the double cones, they have these UV cones which see outside of the normal visible spectrum. But the really cool thing is these oil droplets. So they've got little droplets near the outer segments. Red ones are a different color than green ones, are a different color than the blue ones. And these act like filtered glasses that you might put on back in the old days at a 3D movie to see red and green. These focus the light, they intensify, they filter the light, and they make these cells infinitely more efficient. Birds aren't the only animals that see in the ultraviolet. This is what a butterfly sees. Butterflies really rely a lot upon ultraviolet, not just for finding food, but also for assessing the health of mates. Deer are very reliant on ultraviolet vision. You know, they're out foraging for food at night because they don't have a problem seeing through the snow or seeing in dim light. They can find the ultraviolet signature from food that's on the ground, or they can differentiate between different kinds of lichen on a tree trunk and decide which ones they want to eat and which ones they don't. And also, when there's a layer of snow over the top of it, they can see right through the snow. They also can look at the ultraviolet signature from different urine patterns that animals will leave on the forest floor. So they can look at this and see, aha, this is a predator, this is a wolf, and I need to get out of here, or this is a squirrel and I can hang around. Birds use ultraviolet vision to assess which of their offspring are the hungriest. So satiated chicks give off a different ultraviolet signal than hungry chicks. So mom uses that to help decide who gets what. So rods and cones are not distributed uniformly throughout the retina. This is a diagram of the eye on the left, and you can see that what you're used to seeing, cornea lens. The optic nerve has no photoreceptors on it, so that is the blind spot, the physiologic blind spot. There's one in the other eye, but they don't overlap, so you never notice it unless you test for it. This is the fovea right here. Fovea, Latin for pit, is located along the visual axis here, and you move your eyes or you move your head to point the fovea at whatever it is you're looking at. If you snip this retina here and snip it here and lay it out flat, this is how it lays out. So in the periphery, you get lots of rods, few cones. You get to the fovea, which is here, and you have no rods and all cones, densely packed. This is the physiologic blind spot, no photoreceptors. And then again, the same thing on the other side. So that's how the rods and cones are distributed. This is the fovea, photomicrograph of the fovea of a human. And you can see how there's a pit there, and a lot of the supporting structures, these layers up here are different kinds of cells. They are gone here. This is really pure cones, and with the least amount of stuff that the light has to go through before it excites the cones. Compare that to the foveas of a white-crowned sparrow or a house sparrow, much deeper pit, and the deeper pit does a lot of things. In addition to them having densely packed cones, the orientation of this pit makes it so that they actually have kind of a zoom lens in their eye. And the foveas of the birds and the corneas and the humans are different in that a human has 200,000 cones per square millimeter. Compare that to 1 million cones per square millimeter of a bird of prey. So like 5 times more cones, but it's even better than that. This is the fovea, okay? They got another one over here on the nasal side. So they've got 2 foveas in each eye. One of them, which works in conjunction with the fovea of the other eye, and this one, which works independent, and one in the other eye that works independently. So the reason that that's good is that you can see 3 different areas of very, very sharp vision all at the same time. These are 2 different magnifications. This is the same specimen of the so-called sacred kingfisher, and you see how deep that pit is. It's really remarkable how this thing works. And again, this is just a schematic showing the foveas of an eagle versus the foveas of an owl. Fovea of an owl. Owl has only 1 fovea. So here you are, a bird of prey with your 2 foveas in each eye, flying over the landscape, knowing that you can see a rabbit at about 1 mile. And you can also see a pack of wolves over here, and you can see a vole over on the other side. And the amazing thing is you can see them all at the same time. And so they're able to assess just with the visible light, not say nothing about UV or anything else that they might have, but they can assess what it is they want to go after from a long distance away using this kind of vision. And Bill sent out an email, I know, to all of you, including me, a month or so ago about the hummingbird vision. Hummingbirds have remarkable vision. In addition to the spectral colors of red, blue, and green, they also have non-spectral UV, UVR, and UV, hold on a second, and UVB blue. So, or was that green? Can't remember. Your faces cover half of my slides, so I'm sorry. I'm not reading my whole text, but it turns out that this ultraviolet vision of hummingbirds is responsible for about 30 to 35% of their vision, and they use it to find food, especially in times of scarcity, and to assess mates. They can look at the color of the mate, the UV color of the mate, and make a decision about how healthy or not healthy it is, and whether they wish to have the genes spread by that person. It's not advancing. Hold on a second. I am stuck. Okay, so we can only imagine what hummingbirds see. How many of you have seen Northern Lights?
Yep.
So most people. I think I was 35 years old before I saw the Northern Lights. And what happens is solar wind blows through the outer layer of the atmosphere and excites particles in the atmosphere that get them oscillating, and they emit energy, some of which is visible spectrum. So that's why we see it this way. And this is an outline of the various magnetic fields of the Earth. And it turns out that these magnetic fields that are generated by the Earth, there's polarity, are visible to birds. Light-sensitive cryptochromes, they are called, are able to detect geomagnetic fields, which are responsible for their seasonal migrations and their daily tasks in life. The European robin shown here was the subject of an experiment where you'll see here, taped over the robin's left eye is a goggle to blur the vision. So they blurred the left eye vision, put the robin through certain experiments, blurred the right eye vision, and it turns out that the left eye doesn't bother them at all, but you blur the right eye and they become very disoriented because this geomagnetic field sensitivity that allows them to know where they are in space is governed by the right eye and the left brain. When I was a little kid, one of the neighbors gave me a pair of pigeons. I built a coop, cared for them for about 3 years, and I used to take them to my cousin's house, and when we were ready to leave, I'd let them go. It was like 5 miles. I'd see if we could beat them home, and they always were home way ahead of us because, of course, they fly faster than most cars drive in the city. We know a lot about pigeon flight because pigeon racing is really an important sport in certain parts of the world. The longest pigeon flight on record is 1,100 miles. And average speed is about 60 miles an hour, but they've been clocked at over 100 miles an hour. And before we had the post office, we had pigeon post. And before we had good telecommunications, we had strategic messages sent during wartime by pigeons. So the last thing we want to talk about is the field of vision. So a field of vision is like how much of the world out there can you see at the same time and put it inside of your head. And it's all about the relative size of the retina. If you have a big, expansive, curved retina, you're going to see more than if you have a relatively flat retina. And where are the eyes in the skull? Are they located on the side of the skull or located facing forward? And do you have extraocular muscles or not? And do you use them? So this is a kind of a comparison of the bird vision averaged and the human vision. This as if you were looking down at the visual field. So you see that the left eye has one of the human vision. The left eye sees to the left, the right eye sees to the right, a very large area of overlap where there's a lot of communication between the two eyes. This is where we see our stereoscopic acuity, where we see 3D vision, how we see 3D movies, how you see a stereoscope and so forth. Bird vision on the other hand, is very good for peripheral field, not as good for the overlapping parts of their binocular vision. But again, all birds are not created equal, so we're going to have to go into this a little bit. So the humans are able to expand their visual field by moving their eyes around. So when you move your eyes up, down, left, right, you move your visual field with it. And you do so with this elaborate set of eye muscles, which work beautifully well together. Pigeons and owls see the world very differently. A pigeon has a lot of peripheral vision, very little binocularity. Owls, poor peripheral vision, but excellent overlapping binocularity. And one of the reasons that I think owls are so cool is that they kind of look like us. You know, they have their eyes set in a forward-facing position, and they function very much like humans. This is an owl vision here beneath the photo of the owl, and the diagram of the passerine owl over here, you can see have kind of tubular shaped eyeballs, but they have absolutely no extraocular muscles. They don't, you can't even find them with a microscope. They don't exist. So the eyeballs are stuck in the head, and notice the size of the eye relative to the brain. Pretty remarkable. And the reason that they are able to get away with having no extraocular muscles and having this very relatively narrow visual field is that they've got a really great ability to rotate their head. So they can go a full 270 degrees in either direction. And the rotation compensates for their ocular immobility. Compare this to the neck direction of a human, 80 degrees to the left or to the right. Linda Blair, I think, by the way, could do this 270 thing back in The Exorcist, for all you movie buffs out there. So here we have the owl, and the owl has 14 vertebrae, pretty amazing. Compare it to this human who has 7, and to the giraffe who has, okay, everybody shout it out. How many? 7, right, because a giraffe is a mammal. So it's a mammalian thing. Here we have a peregrine falcon, and you notice how much of the eye, how much of the head is occupied by the eye in its socket. And again, look at the size of the eyes compared to the brain cavity. An eagle, a 20-pound eagle, has an eye that is almost the same size as a 200-pound man. So they really have a remarkable high value that evolution has put on vision for these guys. And so the peregrine falcon also has extraocular muscles too, but they've got this great ability to see detail straight ahead, detail to the side. They can scan, they can do lots of good things. This is a dissection of a peregrine falcon eye with pretty well-developed extraocular muscles. You ever wonder why a flock of birds flying at speed can all aim at a tree and they all just kind of slow down and land? Nobody bumps into each other. Nobody hits a branch and falls out. Nobody gets a corneal abrasion. I mean, how does this happen? I wondered. The best way to explain it is to talk about HD TVs. Okay, so you go down to Best Buy and you say, let me see your TV, tell me about it. They say, well, it's a 4K TV, which with a refresh rate of 60 hertz. Okay, so what that means is a 4K TV is 4,000 pixels horizontal, 2,000 vertically. 4,000 times 2,000 equals 8 million. So you got 8 million pixels on this TV. And the refresh rate is how many cycles per second, how many times does the picture change per second. So cinematic films are shot at 24 frames per second. Most video is shot at 30 frames per second. So the only reason you need 60 or more frames per second is for gaming. And also the changing of the picture sometimes causes a little degradation in the brightness, so that the more cycles per second, generally the brighter picture. So that's for still vision, okay? It says if you've got a lot of pixels or a lot of photoreceptors, you'll have a very good still image. But that's not the way we live, and that's not the way birds live. Birds live at speed, okay? So what's motion vision? Well, motion vision is a whole bunch of still pictures put together. And whether it's a cinema or this little gadget, from 150 years ago, it's still images. And so the function that you need to think about is like the refresh rate, and it's called flicker fusion. This is the speed of vision. It's how many times can the visual system recover per second from a stimulation. So now think about this. Light comes in, goes through all those cells, gets filtered by that little lens, and it stimulates the outer segment. The outer segment has chemicals that move across the membrane, excite an impulse. Impulse goes down the visual system to the brain and comes to consciousness in the cortex of the brain. And then it's got to do it again a whole bunch of times per second. It has to recover. So all those chemicals have to move across the membrane to get ready again for the next one. So how fast can the visual system recover from stimulation in order to respond to the next stimulation? Well, humans, we do it at 60 cycles per second. It's really pretty remarkable, I think. Birds average out at about 100, but a peregrine falcon, because of his ability to dive, and he's speeding fast, he's got to have a faster flicker fusion. And this evolved based on our needs. So the peregrine dives at 240 miles per hour, and he's got a flicker fusion of 129 hertz. Saker Saker falcon at 150 miles per hour, a Harris hawk 150 miles per hour, and who's Usain Bolt, who can plugs along at 28 miles an hour. He is only capable of 60 cycles per second. Okay, we got two more things we got to talk about. The nictitating membrane, translucent membrane, inner eyelid, so-called third eyelid. Okay, some birds have 3 eyelids, some birds have 1 eyelid. Okay, 1 eyelid meaning the nictitating membrane. Some of these 3 eyelid birds close their eyes from the top and from the bottom, some from only the bottom up, some from the top down. So there's a lot of different things, but the one thing that they all have in common is this nictitating membrane, which can be drawn across the eye to keep the cornea moist and to keep dust and stuff out of it. And humans have a vestige of this in something called the plica semilunaris, and I expect every one of you will grab some willing participant when this is over with, and a flashlight and your reading glasses, and find the plica semilunaris in your partner, because it's right here. And this over here, this little ball-shaped structure is called a caruncle. This is a nictitating membrane vestige, okay? And this is the leftover of the third eyelid that covers the cornea. It's an important structural anatomical landmark for surgery. One other thing is the so-called pectin. So if on the left you see a human eye, and the human eye gets a lot of its blood supply from the ophthalmic artery. It gets blood supply from the choroid too, which is behind the retina. But this ophthalmic artery is really important for nourishing the photoreceptors. And birds, which you've heard from me, have this remarkable vision. They don't have surface blood vessels. So you'll see over here in the human eye, you've got these blood vessels that you can see with the naked eye, actually. And in between the ones that you can see are almost invisible. They're microscopic, tiny capillaries, so that the capillaries are flowing all through the retina, or blood is flowing all through the retina via these capillaries. But there's a cost to that in terms of image resolution. So it's just yet another layer that light has to go through in order to get to the retina. So birds figured it out, and they have this thing called the pectin. And the pectin is a comb-like pigmented structure, blood vessels, and some other organelles that projects into the retina, kind of like the blind spot, the physiologic blind spot. Doesn't seem to affect their vision at all because it's the other side compensates for it, the other eye. And this is able to nourish the retina and adjust the acid-base balance of the vitreous. And so if you're like me, you say, God, these birds are unbelievable. How did they get to be like this? And I'm thinking, like, I thought we were running this planet, okay? We can make movies about birds. You know, they don't make movies about us, but their vision is so great. Well, how did this happen? Well, we've all heard, and you guys probably all know this, I didn't, but I've heard birds are the closest ancestor or the closest descendant of their ancestral dinosaurs. Okay, that and it's and that's not quite true. The birds have this superhuman vision, like they see outside the visible spectrum like Superman, and they see in slow motion almost with that huge flicker rate like the Flash. And the reason for their ability to do this is that if you look at these two skeletons, this one is a Corythoraptor, a dinosaur, and this is sort of the average bird skeleton. And you see the incredible similarities because in the age of the dinosaurs, we had flying feathered dinosaurs sharing the same planet as the giant dinosaurs. So birds are not descendant from dinosaurs. Birds are dinosaurs. The oldest modern humans, if you, depending on where you choose to drop your push pin, is either 300,000 years ago or 6 million years ago, depending on how far you want to go back. If you go back to even our common ape ancestor before humans split off, that was 6 million years ago. Okay, so say, well, they already had vision then. How about before that? Well, if you go back to Mesozoic time, the mammals, pre-mammals that shared the earth with birds and dinosaurs were these little mouse-sized, basically rodents who survived the asteroid crash and were able to ultimately evolve into mammals. But if you look at this developmental tree here, you see we got way over here, you got birds evolving along with all these other guys. And the birds developed a great survival strategy in that when the asteroid hit, killed off photosynthesis, killed off a lot of the food sources for the animals of the earth, birds were able to survive. Birds and other little animals. And they were able to migrate. They had a lot of stuff going for them that were competitive advantages that the big dinosaurs didn't have. And so that's really all I have to say, except that, let me go back here. The birds had at least 130 million year head start on us. So I think that's the reason why their vision is so incredible, is that they've been at it for a lot longer than we are. And so I'm hoping that humans can live for 130 million years and develop the same sort of vision that birds have. So what is this? What kind of bird is this?
Painted bunting.
Cat, not you, Ed.
Painted,
Everybody else
painted
is painted bunting. So that's all I have to say tonight. And I thank you for your attention and happy to entertain any questions you might have.
Thank you, Dr. O'Malley. Up at the top of the screen, you'll see a little green thing that says you can stop, or a red thing that says you can stop sharing.
Stop.
There we go.
Good.
Well, thank you very much for that presentation. The only thing that I can think of when I thought of that presentation was Annie Lindsay had, or probably still does, a T-shirt that says "Birds Rock." And, after watching that discussion about, how superior the vision is in birds, yeah, they really do. So anybody have questions for Ed O'Malley, our speaker?
Come on, somebody.
Well, I'm going to start while other people are formulating their questions. So there are humans on Earth who are like super tasters, essentially. Things that are bitter are like 100 times more bitter to these super tasters. So birds really are, in terms of, comparing it, they're like super seers compared to us. Would that be, I think, a really good way to think about it in comparing them to humans?
Well, I think the super tasters are they're part of a bell-shaped curve of tasting and smell, which are kind of the same thing. So you got some people like, you know, the Ben and Jerry's guys. Ben has a terrible sense of smell and he's very bad at tasting. Okay. But he's really good at texture. So he can hardly taste, but his partner, fortunately, made up for it. So there are people on this earth that have very highly developed senses of taste, which I don't think it's quite like perfect pitch, you know, where you're just born with it and you don't know why you have it. You can't really play the piano, but you can tell you what a G sharp is. And it's not that. It's that I think that taste and smell probably is a bell-shaped curve, and some people are really, really good at it, and some people aren't really, really good at it. But you can. Comparing the bird's sight to that, I think is selling the birds a little short.
That's good. Bill, I have a question.
Yes.
In your research, which bird has the best vision?
Probably the peregrine falcon. Again, best is sort of relative, because if you mean compared to the way that we see, the peregrine falcon is the best. But the owl and other nocturnal hunters, they have remarkable vision at low levels, so that, you know, it works for them. But the day hunters, the predatory falcons are really it. Bald eagles, all the eagles are really good.
Okay, and I'm going to counter that with which bird species has the worst vision?
You know, I don't know. Let me think about that. I think that you could probably take any bird and find something that that bird does way better than we're expecting it to do. So that even if you think about a sparrow, you know, sparrows are kind of like, you know, they're so common, so we don't think very highly of them, but they have really remarkable vision, remarkable ability based on their foveal anatomy to resolve. And they have side-mounted eyes, so they have this tremendous peripheral visual field. You know, I think if you made it into the bird club, you know, they have a vision test, you know, right at the beginning of it, just like your driver's license. And to get in the club, you got to have really good vision. So I can't think of one that's bad, but there must be.
Right.
Hey, Dr. O'Malley?
Yes, sir.
What about penguins? Penguins, you know, are different. Their area is water as opposed to air. Does that have any effect on their vision, because they're chasing around anchovies and different things? So
Sure.
what do they have that would be different from an air flying bird?
Yeah, I don't know that, but because I didn't specifically look at any penguins. But if you think about, penguins evolved where their ability to see lots of different colors is probably not very important to them. They're living on ice. Okay, and then when they dive in the water, they are looking. It's a kind of a monochromatic blue to us. They probably have ability to see within that narrow wavelength of light that we see as kind of blue-green. They probably can split out a lot of different colors and use their UV vision also. But I don't know that for a fact. But again, you know, Usain Bolt has a refresh rate of 60 cycles per second because he only goes 28 miles an hour. The penguins don't go 28 miles an hour. So I have a hunch that their refresh rate is not very high either.
Thank you.
Mm-hmm.
Okay, I had two questions.
Yes.
First question, how can you prevent birds from running into your windows?
Oh, stay tuned. Next month's speaker is going to address that very thing.
Thank you very much for that plug.
Very good. Very good.
Thanks, Jimmy.
Any tips?
Bill, tell us who that is.
Well, our speaker next month is Nick Liadis, who is a research fellow at the Carnegie Museum of Natural History in Pittsburgh. He was supposed to be our speaker last March, before all the COVID madness happened, but he'll be joining us from Pittsburgh next month. The meeting will be on October 19th, of course, via Zoom. You'll all be getting a link to that meeting. Thank you, Mike and Judy, for allowing us to piggyback on your account. Roseanne just sent me a text and said, way to keep birds from running into glass. She says birdsmartglass.org. You can find more information there. Are there any final questions for
You could also paint the windows.
Yeah.
I have a
That's an
question.
idea.
Hi, can I ask a question?
Yes, go ahead.
Hi. Let me turn on my video. Hi. Regarding the refresh rate of the vision, it looked like the slide went quite fast, but it looked like we are quite slow compared to our refresh rate, eye refresh rate. So why is there, what kind of evolutionary pressure was there for our eyes to have such a high refresh rate compared to how we live our lives? It almost like
it seems like it's too high, right?
Drive cars.
Yeah. Yeah, it does seem like it seems like 60 cycles per second is too high, but I think we're just lucky.
Okay.
Yeah, but I mean, the important thing is, relatively speaking, for the organisms like birds that travel faster, and I'm sure cheetahs, and if you've measured, the really fast animals, ground animals, you probably find high refresh rates on them too.
I have a question. Was there anything that was particularly surprising to you that you discovered as you did your research?
I wasn't aware of the refresh rate because we don't think of that very often in ophthalmology. It's just kind of it's just there all the time, and there's not much difference in the flicker fusion of one person to another. There are some diseases in which the flicker fusion is affected, but unlike birds, who, if you put them in a coop with fluorescent lighting, might get very agitated because of the flicker of the fluorescent light that they see that we don't. That's the whole flicker fusion thing was surprising to me, because frankly I haven't thought about that once in the practice of human ophthalmology.
All right, I think Tommy has a question.
Yeah, why are bird eyes different colors?
Well, I'm not sure where the why. I can tell you how bird eyes have different colors. The colors are based on pigments in the iris of the eye that absorb and reflect light. So, for instance, melanin is kind of a brown pigment, and there are certain yellow pigments that are in the eye. There are some green pigments in the eye, but mostly the iris of a bird would be yellow or light brown or dark brown. But you may see blue-eyed birds or white-eyed birds. So a bird with a white iris is one that has no pigment in it. It is reflecting all of the incoming light. And all light, if you put all the wavelengths of light together, they bounce back as white. Okay, so white light contains all the colors. Did you ever, in your science class, you ever hold a prism in the path of a light and see the light be broken up into its component colors? You ever see that? Like a rainbow? No? Oh, you will. Okay, so white light has all of the colors. And in the case of an eye that doesn't have any pigment in it, if the iris is thin enough and it has a network of protein fibers, it will actually reflect the light in such a way that the high energy blue light is reflected back to you, preferentially over the other wavelengths of light. So the eye looks blue, kind of like feathers. Like a blue jay doesn't have blue feathers. If you pluck a feather of a blue jay, look at it under a microscope, there's no pigment in it. It is transparent. And what it is, it has a molecular structure that's like a prism, and it manages to reflect back to the eye of the observer the blue pigment, the high energy blue light. So, that's sort of a not a great answer to your question, but as to why they have developed, well, the why is always what's worked for the organism given the push of the environment. So what do they need, and what adaptations are helpful for the organism to survive? And one would assume that the color of eyes is the result of some environmental push and the organism's natural adaptation to it by mutations. So it's sort of like the organisms on the earth are perfectly designed for the job that they are doing today, but tomorrow it might all be different. And because we're continually under a constant state of evolution, but it's just happening so slow that we don't see it before our eyes.
All right. I think Albert Biglin may have had a question. Let's see. Albert, are you mute? Are you on mute?
Yes, I am.
There we go. Good.
I changed my microphone. Can you hear me better?
Yeah,
Oh,
perfect.
much better.
Okay. Let me put a plug in. 2 weeks ago, my wife and I went out to the Powder Mill Nature Reserve, which is part of the Carnegie Museum of Natural History. We observed the bird testing for windows. Birds bumping into glass windows or your window in your house or your patio door. It's a very big problem, and there's a lot of death. So they have windows being sent with all sorts of different patterns on them. And they have a cage, which is a tunnel, and the bird flies into it, and they'll try to get out, and they will avoid the ones with certain designs in the windows. And it's a fascinating area. It's one of the international bird banding places. They catch birds and put the little bands in their feet and let them fly. Fantastic place. You will have a very exciting event next month.
Terrific. Annie knows nothing about that place.
Thanks for the plug. I'm sure that Nick is going to show some pictures of the tunnel.
Very good. All right. Any other questions?
When Ed talked about the nictitating membrane and referred to a residual nictitating membrane that humans have?
Yeah, the vestigial. So it's what's left over from when we stopped having nictitating membranes.
Wow. So when we were reptiles?
Yeah, well, when we were somewhere in our past, we probably had something that was like a third eyelid.
Interesting.
Well, thank you very much for your time this evening, Ed. We really,
My pleasure.
I found it absolutely fascinating. I hope everybody else did.
Thanks to all of my friends who tuned in too.
Thank you very much, Ed.
I'd like to thank Mary Rock and everyone else who contributed coffee and cookies to previous meetings. And I look forward to sharing those with you personally in the future. As I mentioned earlier, our speaker next month is Nick Liadis, and we'll be sending out a link to the meeting about a week prior to the meeting so that everybody will have it. Those of you who attended the meeting tonight for the first time, I hope you come back in the future. I think if you get into the room with us, you'll find that we're welcoming, and we're happy to share our information and our knowledge, and we do not bite. So any last something good for our organization? Anything else?
We have a membership form on the Facebook page.
Thank you very much, Ed. We have a membership form on the Facebook page and on our website. Our website is gpaudubon.blogspot.com. gpaudubon.blogspot.com. Okay.